In this video, we'll be looking at the third type of problem involving transformations, and that's where we're given the graph and we have to decide what function did I start with and what transformations happened, and based on that, what function do I have? Okay, so I know it doesn't say to do all that, it just says find the function that's graphed, but in practice the way we do that is by finding where we started, finding what happened to that graph, and then using that to define the function. So in this case, let's do this one together. It has a big V shape, so I know my parent function is just going to be the absolute value of x. So let's start with that. 0, 0, 1, 1, 2, 2, etc. Okay, negative 1, 1, negative 2, 2. Okay, so that's my parent function. I just need to decide visually what happened to get me from this guy in green to that guy in black. Well, the first thing I can see is that at some point I shifted everything down by a few units. So 1, 2, 3 units down. Okay, so let me go ahead and draw that. 3 units down, if I took 1, 1, that would become 1, negative 2. 2, 2 would become 2, negative 1. Negative 1, 1 would become negative 1, negative 2. And negative 2, 2 would become negative 2, negative 1. Okay, so let's see. I've got absolute value of x. I have a shift down by 2, but then there's still a difference between my graph in red and the one they have in black. The one in black is much steeper than the one I have. So the way I want you to think about trying to find stretches and shrinks is by comparing the steepness. So let's pick out some specific points on our graph, or we can also see some corresponding points on the graph in black. In my graph in red, I want us to think about the steepness, or you could say slope, of this little segment right here. So it went right 1, and it went up 1. Let's compare that with the steepness on this guy in black. On the one in black, it went right 1, and it went up 1, 2, 3. Okay, so to get from the function I have in red to the final function in black, the steepness, or in other words, basically how much steeper did I make it, going to be 3 divided by 1. Both of them went right 1, but our new one in black is 3 times as steep. So that's going to be a vertical stretch by a factor of 3. Because again, it is 3 times as steep, 3 times the slope there. So I have these two transformations here. It shifted down 2, and it did a vertical stretch by a factor of 3, but we always do our shifts last. So the next thing I'll do is a vertical stretch by 3, and saving it for last, I'll do that shift down 2. Okay, so to vertically stretch by 3, the whole function gets multiplied by 3. To shift down 2, I'm going to take the entire function and then subtract 2. So my final answer here, the function that was graphed is 3 times the absolute value of x minus 2. And let's take a second just to double check that. Okay, so I'm going to do 3, math menu, go over to absolute value, times the absolute value of x, and then on the outside, minus 2. Let's see how that compares with what we graphed. I'm expecting points like 0, negative 3. Whoops, sorry, I'm not sure why I wrote down 2 there. This was a shift down 3, so let's go ahead and clean that up really quick. Okay, I was saying that, but then for whatever reason, I wrote down the number 2. Alright, so that's a shift down 3. Okay, let's clean that up then on the calculator. And this is part of why it's good to go ahead and check it on the calculator. That can help me spot any mistakes I've made. So I'm expecting points like 0, negative 3. Let's see if that one shows up. Yep, 0, negative 3. Points like 2, 0. Or sorry, 1, 0, there we go. Yep, and negative 1, 0. Yep, sure enough. Okay, so we see that function there. And my final answer, now that I've actually cleaned it up, 3 times the absolute value of x minus 3. Okay, so that's our first example of this. What I want you guys to do is see if you can apply that knowledge to solve a second problem. So thinking about what we did in this first one, we identified, based on the shape, what was the parent function. Then we brainstormed which transformations do I see. We pieced all those transformations into a coherent order where the shifts happen last. And then we used that to come up with the definition. And as an extra added step to make sure we did everything right, we went ahead and graphed it too, and that helped us find a mistake. See if you can apply those steps here, so go ahead and pause the video, try it out, and then unpause to compare your answer with mine. So based on the shape, the only one that starts at a point and does a gradual increase is the parent function square root of x. So I know I'm starting with that. So let me do a quick sketch of that graph. That would be 0, 0, 1, 1, something over here like 4, 2. Okay, so definitely some things have happened to get me from the one in red to their final graph in black. One thing I can see that's happened is they've reflected this guy across the y-axis. So let me show what that would look like. Okay, so I would have negative 1, 1. I would have, instead of 4, 2, negative 4, 2. Okay. Now, let's see if I can spot an exact point on this final guy in black. I'm seeing this point right here, which is the point negative 9, 1. So for this one, I see that my steepness, it went over 9 and up only 1. I want to see what would happen on this graph in blue if I went over 9. Okay, so let's get a little bit more specific. I didn't graph this specifically before. But let's go back to the original and add some points. 1, 1, 4, 2. I would have way over here 9, 3, which means way over here I'd have negative 9, 3. So let's compare those guys. Okay, in the final function it went left 9 up 1. In this previous function it went left 9 up 3. So if I'm comparing those steepnesses, it's a new steepness of 1 and an old steepness of 3. Okay, so the stretch or shrink here is actually going to be 1/3. It is squattier and shorter than it used to be. So the things that we see happening, we have the parent function there. We had a reflection across the y-axis, and we had a vertical shrink by a factor of 1/3. And it really doesn't matter what order we pick here. Okay, because there's no shifts, I don't have to worry about doing the shifts last. So I'll just do the order I've already written it down. Reflection across the y-axis, and a vertical shrink, or you could just say a shrink, by a factor of 1/3. So let's define those guys. Reflecting across the y-axis, you take the function and plug in negative x. Vertically shrinking by a factor of 1/3, you take the entire function and multiply it by 1/3. So the function we've graphed here is 1/3 times the square root of negative x. Let's confirm that on the calculator. Always a good idea. Okay, so my function is 1/3 times the square root of negative x. And let's see if that looks like the function that they gave us on the graph. Okay, so it should go through points like 0, 0 and negative 9, 1. So let's try that. 0, 0. Yep, how about negative 9, 1? Sure enough, it looks like I got the right function there. Okay, so don't be afraid to go back and check at the end. Like we saw in our previous example, sometimes if we've just made a silly mistake and written down a wrong number, it can help us identify that we didn't do it correctly. Or if we did it correctly, it can help us confirm and feel more confident that we really did pick that right sequence. Okay, so thinking about some important things here, recurring theme, if we pick the order, you want to make sure that the shifts happen last. By comparison, if the problem statement tells you the order to do those transformations, then we're not picking the order. You shouldn't change the order in these cases. Just follow whatever they tell you. It's only when we pick the order that we want to make sure the shifts go last. And that's just the best way to fit our intuition to what works well for functions.